Hello, this is Dr. DA. It's great to be with you guys again. And we are going to continue our discussion of the quantum model. And to do this, we're going to go back to our PowerPoint where we left off last time. We had talked about how, according to quantum theory, electrons are described by a wave function called psi. And this wave function consists of essentially a description of the electron's energy and probable, location or region of space where it might be around an atom. We said that the wave function relies on three quantum numbers, and then later on a fourth one was added, and they'll give us particular information about each electron. And each electron in the atom is actually described by a set of unique quantum numbers. So we're going to talk first of all about what these so-called orbitals look like. Of course, the word seems to suggest perhaps like an orbit, right? But it isn't. So let's talk about the shapes of these orbitals, all right? Remember that according to the Heisenberg principle, we can never define the position, the path of an electron exactly. So what a wave function does is it allows us to calculate the probability of finding the electron in a given volume of space. And this probability is related to the square of the amplitude of the wave function. Now remember, we are talking not about a one-dimensional wave like the ones we started out discussing when we first learned about the properties of waves. This is a three-dimensional wave function. And in 3D space, what you can do is you can generate what's called an electron density map, something like this. This is actually the accumulation of a bunch of dots where you would be calculating what is the likelihood of the electron being in this particular region of space around that center dot, which is the nucleus, all right? And notice that because of the probability distribution, we sometimes think of the electrons as forming a cloud. Excuse me. Now, one of the approaches that I can take is I can take this cloud and kind of slice it up into kind of like onions slices and calculate what is the probability at each one of these slices, and then map out the probability with respect to the distance to the nucleus. All right. And then what I can do is I can wrap up what would be the region of space for this particular orbital, which is actually a 1s orbital, where there's 90% of the density of electrons, or 90% of the probability of finding this electron. And then I can draw a graph that looks like this. This is called the radial probability. In other words, at any distance from the nucleus, what is the likelihood the electron will be there? It's interesting that the maximum of this distribution occurs right about 53 picometers, which is actually the radius that Bohr calculated for the atom of hydrogen for orbit n equals 1. So it's interesting that it matches that model. One thing you might ask is, you notice that at zero distance from the nucleus, the probability is zero, right? Well, it makes sense. The electron is never inside the nuclear space, right? Okay. So let's look at what happens when the value of n increases. Remember, the one we just saw was for n equals 1, which is the first subshell. And for an s orbital, now what happens when n increases? And we're going to leave the value of L at 0 for all these analysis here, all right? Notice that now, as the value of n increases, you look at the shapes on the top, and you notice that it looks like there's, kind of like spheres hidden within spheres, but then there are spaces in between them. In the radial probability graphs that you see on the bottom, you can see how in going from the first example to the second one to the third one, you can see that there are multiple peaks, multiple regions of higher probability. And actually, the bigger the value of n, 1, 2, 3, the farther away the largest peak is. Remember we said that the value of n tells us information about how far the electron is from the nucleus. Just remember that this is not an exact position, it's more like a region in space. And it turns out that that particular slice, for example, for 3s is farther away than it is for 2s, which is farther away from 1s, right? Now, notice that the shape of these orbitals is actually sort of like spherical, right? And also notice that for the 1s, the peak of higher probability is no longer at 53, 54 picometers. Well, that's because this is not going to be a hydrogen atom. In order for you to have values of n bigger than 1, you are going to have to go to more electrons in the atom. So this would not be a typical hydrogen atom. All right. Okay. Notice that for all of these, like I said before, the value of L would be equal to 0. And this is what we call an s orbital. So what it tells us is that for any value of n, any s orbital, in other words, any orbital where s, the value of L equals 0, the shape of these things is like a spherical cloud, with the majority of the probability being farther and farther away as the value of n increases here from 1 to 2 to 3. Notice also that because L equals 0, the value of ML, the magnetic quantum number, has to be 0 also. In other words, anytime you have any s orbital in any shell, 1, 2, 3, there's only going to be one of those s orbitals. Now, what happens when the value of L changes? For example, we know that L equals 1 corresponds to a p orbital. If you do the same analysis and plot out the electron density, what you get now is no longer a spherical distribution. It's more like a set of lobes. And you can see the top part, the electron density. And if once again, we kind of like put a little boundary around the region of space that would contain about 90% of this electron density, you can see that you generate the shapes on the bottom. These two kind of balloons or lobes, which contain about 90% of the electron density. In other words, the probability of the electron being in those regions in space. Notice that there's a node in between the two lobes. In other words, the electron has about the same probability of being one side or the other one, but it's never in the middle. So in other words, it's not like it travels from one lobe to the other, like the way gas particles would travel from, let's say, one tank to another one. This is just a wave that is oscillating in space within these regions of probability. Now, with L equals 1, that means that ML, the magnetic quantum number, can have three values, -1, 0, and 1. And what that means, therefore, is that there are three different ways in which the p orbitals can be oriented. And you can see them here for the three different possible values of ML. They can be oriented along the x, or along the y, or along the z-axis of three-dimensional space. You are not required to memorize which value of ML corresponds to which orientation. Just remember that there are three of them, and they basically vary in which axis of three-dimensional space they are oriented along. Another thing is, if L equals 2, in other words, this is when you had d orbitals, now ML has 5 possible values, -2, -1, -0, +1, and +2. And these correspond to 5 possible orientations of the lobes, which, as you can see here for the D subshell, they have like different shapes. They're like mostly like 3 or multiple lobes, and some of them oriented along different planes. And there's, of course, there's one that's kind of a weird double lobe with like a ring kind of around the middle. Again, you don't need to memorize which value of ML corresponds to which particular d orbital. Just remember that there are 5 possible d orbitals, all right? So as we see, if we build a table, we can see that for every value of n, you have a corresponding set of values of L, which are limited by the rules we discussed last time. And in turn, each value of L is limited by, each value of ML is limited by the value of L And that's how you can calculate how many orbitals you can have in each one of those subshells. So you can designate them the way they're designated here in the last column. You can see, for example, let's say for the 2p orbitals, you would have essentially 2px, 2py, 2pz. For the 3p orbitals, you would have 3px, 3py, 3pz. And notice that only when you reach level 3, n equals 3, that is when you're allowed to put in d orbitals. And in the same fashion, when you get to level 4, you'll be able to also add f orbitals, which we will not discuss in this course because atoms that occupy those kinds of orbitals are typically unstable, and they are usually like in the bottom of the periodic table. All right. Okay, so let's summarize a few things we discussed here. So the wave function of Schrodinger essentially gathers 4 parameters, right? An electron is going to be defined by 4 unique values. In other words, a set of 4 unique values. Any electron that has the same value of n is said to be in the same shell or level. If they have the same values of n and l, we call that a subshell. So that would be like a s or a p or a d sublevel or subshell. And if electrons have the 3 same values of n, l, and ml, then they would be in the same orbital. Now, the question we have to ask now is, how many electrons can one orbital hold? Okay, remember, an orbital has a unique value of n, a unique value of l, and a unique value of ml, right? So the only parameter that you can vary then would be the spin number, the ms, and that has only 2 possibilities, +1/2 or -1/2. So in other words, if an electron is in a given orbital, it could be NLM and then +1/2, or it could be NLM and -1/2. In other words, there's only 2 possible values allowed in one orbital, which means therefore that in one orbital you can have a maximum of 2 electrons. Okay? So let's do a little practice here. Let's ask ourselves, how many electrons can be placed in the 3D subshell? Let's think about it for a moment. When we look at that designation 3D, we have several pieces of information here. First of all, the number 3 tells me that the value of n equals 3. The designation of d, as in d orbital, means that the value of L equals 2. Now, if L equals 2, that means that ML, in other words, the possible orientations, the possible orbitals you can have in this subshell are -2, -1, 0, +1, or +2. In other words, you can have up to 5 orbitals in this particular subshell. And since each orbital can hold up to 2 electrons, the maximum number of electrons that you can put in the 3D subshell would be 5 times 2 for a total of 10 electrons. Okay? When you start doing the math of these things, and I don't want to go into that in detail, but you can come up with some interesting relationships. For example, in any given level, the number of sub-levels is going to be the same as the number of that level. Think about it. Walking your minds through levels 1, 2, and 3, and you'll convince yourself that that is correct. The number of orbitals within a sub-level, 2L plus 1, right? Because you can have any value of L, you can have -L and +L, right? So that's 2 times L. But you also have 0, so you add 1 more. And here's another interesting one. If you want to know how many orbitals are in a level, you can just basically take the number of the level n and square it. So these are kind of little things that you can play with and you can test them out by yourself. So I'm not going to go deep into that. The other thing that I was going to bring up is, when we look at those orbitals, we notice that except for the s orbitals, right? Except for the s orbitals, all of the other ones have these weird lobed shapes, and some of them oriented in different ways. So why are atoms spherical? Because we said back in chapter 2 that those experiments with the scanning tunneling microscope revealed that atoms are in general spherical. Well, here's an example of an atom where we've put in several levels and sub-levels. You cannot see the 1s in there or the 2s, but we're going all the way to the 3s here, which would be the large, bluish kind of spherical shape around there. And you can see everything else contained in it, all the lobe structures. So you can see how when you mix them all in, you blend them all in, you actually end up getting a kind of like on the average, some kind of a spherical shape. Okay? Okay, so now let's talk about how the atom is built. We're going to talk about the architecture of the atom. So one of the things we can do is we can correlate all of these different levels and sub-levels with the energy and draw some kind of energy diagram. So let's start out with a hydrogen atom, which has only one electron. This would be a typical diagram. Remember that we said that if we consider a wave function oscillating between two boundaries, and in the case of an atom, the boundaries, according to Bohr, would have been an orbit. It would be a circular kind of boundary. We generated these different energy levels. They are not equally spaced. As you go higher in energy levels, the next level is a little closer, so there's less difference in energy between one and the next. But in this model, we can see that the energy depends only on the principal quantum number n. So for example, 3s, 3p, and 3d, all of those subshells would have the same energy. And that's why in a hydrogen atom, you see only the transitions that we earlier analyzed, which simply depend on jumps between levels, right? So again, the energy is given by that Bohr function that has to do with that modified Rydberg constant, right? And then you'd have a progression here of levels n1, n2, n3, which is kind of like we discussed before. Now, what happens when you build an atom that has more than one electron? Well, it turns out in a multi-electron atom, the energy depends both on the value of n and the value of L. Both of them are important. So you can see here where within each subshell, there are small differences between them. So for example, n equals 1, L equals 0, that would be the 1s orbital. 2s orbital would be n equals 2, L equals 0. 2p subshell would be n equals 2, but then L equals 1. And we can go on and so forth, going up here. Now, several things might jump at you here, all right? And again, don't forget, s orbitals means L equals 0. P orbitals means L equals 1. And d orbitals means L equals 2. Now, a couple of things here are interesting. First of all, why these differences in the sublevels themselves? Why are those two different there? The other one is, notice that the 3D subshell is actually higher in energy than the 4s. In the previous model with one electron, that wouldn't have happened. Basically, the energy depended exclusively on the value of n, 1, 2, 3, 4, 5. But in this model, it turns out that the 4s subshell is lower in energy than the 3D. All right, so let's start out by explaining that. Let's go back to our radial distribution function. Remember what we did was we plotted out, we mapped out what is the probability of the electron being at a certain distance or radius from the nucleus. And then we took that and we made a plot where we plotted that probability against the distance from the nucleus. And like we said, in the case of the 1s orbital for a hydrogen atom, the maximum probability occurs around 52.9, 53 picometers, essentially. That's kind of like where an electron in a hydrogen atom is most likely to be found. That's kind of like the overall, let's say, radius of this spherical electron cloud. And the electron is oscillating within that region of space, mostly with its density being around 53 picometers. Now, what happens when we go to, let's say, levels 2 or 3? We said that now you have this kind of like a onion layer kind of model. And I'm sorry, this is kind of small in there, so I hope you can see it well. But if you look at the radial distributions down here, what you notice is that there are multiple peaks of probability. You can see, for example, for the 2s, there's 2 of them. And then for the other one, you have 3. But notice that although the majority of the probability is occurring at, let's say that distance or that distance from the nucleus, there are some minor regions of high probability or high density a little closer to the nucleus. This phenomenon is called penetration. Essentially, it means that for a given orbital, there may be regions of electron density closer to the nucleus, although not as dense as the main layer of probability. Now let's see 2 models here. On the left, I'm showing, let's say this is an atom with 3 electrons. So let's say this is lithium. Notice that you'd have 2 electrons occupying that 1s orbital and then 1 electron outside of it. Notice that if the electron is on the outside of that electron cloud occupied by those 2 electrons are definitely enjoying the benefit of the interaction with the nucleus. And remember, anything that goes in favor of an electrostatic attraction lowers the energy, makes it more stable. Now, what is happening is that electron cloud is slightly repelling the electron on the outside. So essentially, it's almost as if of that +3 charge on that nucleus, 2 electrons in that inner cloud are kind of blocking some of that charge. And so the electron that's on the outside is only experiencing the equivalent of about 1 positive charge. So that means that it is not as stable. On the second drawing on the right, you can see the effect of penetration. Let's say that that electron, that third electron, is capable, at least some of the time, to be located inside the electron cloud of the inner 2 electrons. Now that electron has full access to the complete +3 charge of the nucleus. And so it offers an advantage energetically versus the model on the left. All right? Okay, let's look back at our probability density distributions here. Okay, what I'm showing here is, again, at different radii, picometers from the center, from the nucleus, what is the total probability? And you can see the 1s, you can see the 2p, and you can see the 2s orbitals in there. All right? Now, here's what's interesting. Look at the 1s orbital. It's kind of like almost like a barrier. It's very dense and very close to the nucleus. That is a very stable location because, or region, because it offers, maximum access to the positive charge of the nucleus. Next comes the 2p. Notice that calculation-wise, the 2p orbital has a region of high density that is closer to the nucleus than the main region of density of the 2s orbital. You can see it there, right? But notice that the 2s orbital has the capability of penetrating. It can penetrate into the area or into the region that is currently being, taken up by the 1s orbital. Therefore, electrons in the 2s subshell are able to penetrate, and even though it's kind of a little small there, you can see where they are able to be closer to the nucleus and experience a greater attractive force. The electrons in the 2p sublevel, on the other hand, they're pretty much excluded. They're pretty much outside that electron cloud of the 1s orbital. So they are kind of getting repelled, and therefore they're shielded from the full attractive force of the nucleus. As a consequence, because of this ability to penetrate, the 2s orbital ends up having lower energy, in other words, more stability than the 2p sublevel. Now, because these levels and sublevels and their energies are probably not something that it's easy to memorize, you can build a little chart to show the order in which the orbitals would fall in an energy diagram. So what you do is you write out, first of all, level by level, by sublevels. You have the 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d. So you kind of like write them first of all in straight lines, little boxes here. And then what you do is, beginning with the 1s, you're going to start dragging kind of northwest and zigzagging back. So this goes here, and then there, and then back. So you can see how the zigzag motion goes, right? And that tells you that after you've made this turnaround 3s into 3p, notice that your next orbital is actually going to be that 4s orbital that you saw in that diagram before. So I would say, you know, if you can maybe have this like a cheat sheet or just a print of this page here, you'll be able to remember the order in which these things are filled. That being said, all right, we're going to later on in the next lecture learn a little shortcut of how to do this without having to actually memorize these things, okay? So just fair warning that there are better things to come, all right? Now, the other thing we'd like to do is, rather than write, you know, the quantum numbers for every single electron in an atom, what we'd like to do is come up with a form of expressing, well, what is the architecture of a particular atom, of a particular element, all right? And this is what we call the electron configuration. It's going to tell us how are the electrons distributed amongst the various orbitals in an atom, all right? So this is the format of an electron configuration. So let's look, for example, at hydrogen with one single electron. This would be the electron configuration, okay? So look at the way it works. The number 1 would represent the value of n. In other words, this electron is this, I'm sorry, there is an occupied or partially occupied first level. The s represents the sublevel, or actually the value of L, which in this case, L equals 0, because that's what corresponds to an s orbital. And this superscript tells you how many electrons are in that particular orbital or subshell. All right. Now, the thing here is, as we go on later on, we'll see that the superscript really only tells you how many electrons are in the subshell. It doesn't specifically tell you, in a subshell that has multiple orbitals, how they are distributed among those orbitals. So we'll have to work on that later on. Another way of representing this by drawing what's called an orbital diagram. And in this case, what we do is we draw the orbitals as a little box, all right? And so for hydrogen, we draw one box, and we put a little arrow in there representing the electron. Now, why do we use an arrow? You know, it's kind of a symbolic way of representing the other property, right? Remember the value of the spin number, ms, which is essentially plus 1/2 or minus 1/2, or as we sometimes say, spin up or spin down. So this is just a way of representing the electron as an arrow, just to signify that this particular one we're drawing here is spin up. Okay, now, what we're going to do now is we're going to start building atoms. So let me move out here. I want to show you something which hopefully you were able to see in our module. I posted in there a couple of different forms, okay? So this is one of them. I'm going to show it to you right now. This is a document that's available in your Canvas module, where I have multiple copies of the diagram I'm going to be using during this particular exercise. So you can print this out and then fill them in one by one as we go. Unfortunately, these are actually just images here. These are just pictures. So, I mean, unless you have the software, you can't just draw or write in there. So you'd have to do it by hand. But if you have the software, hey, knock yourself out. You can do it, all right? All right, let me show you another version of this that I have. It's in a Word document also. And this one is a, let's see, this is called a fill-in mode. So this one just has in the whole page, let me zoom out so you can see what I mean. Okay, so this is the whole page of the document, and there's room for one of these things. Now this one is already set up where you can actually put things. So what I did was I put these arrows here. These are actually just images. So what you can do is you can copy that, right? You can copy it, And then if you want, you can paste it. And then what you can do is you can grab that guy and, oops, sorry. You can grab that copy and move it around if you want, wherever, you know, if you want to put it down here in the 1S, it'll let you. So you can play around with it and move it around, okay? So the only thing with this model is that this only has one of the sheets. So you'd have to copy the whole thing into other pages so you can do multiple forms. So I'll let you guys decide how you want to do it, okay? No rush, no problems. Or you can simply just follow along our presentation here. So this is again the drawing, and what I'm going to do is I'm going to take the first 10 elements in the periodic table, and I'm going to take their number of electrons and place them on this diagram. And this is called an Anbau diagram. Anbau essentially means something along the lines of, you know, building up. So we're essentially going to build our electron structures here by putting in little arrows to represent however many electrons we have in an atom. For example, let's start with the first one. The first one we're going to do is going to be hydrogen. Okay, so hydrogen has 1 electron. So the principle here is that you have to start placing the electrons in the lower energy levels and then work your way up. So I'm going to put them in there in the 1s subshell. I'm going to put it spin up, but I don't have to. I could put it spin down. So the idea is that as we add more electrons, we're going to be putting them, you know, starting with the lower energy levels and moving on towards the higher energy levels. Oops, sorry about that. That didn't look very good. Let me erase that. That's not very good. Okay, let's go back here. Let's bring it here. I don't know if I can draw a straight line. Kind of like that way, right? There you go. I sometimes call this the Drake model. You know, started from the bottom, now we're here. Anyway, so what we have here then is electron for hydrogen. So the electron configuration will be 1s1 because we have 1 electron in there. Okay. Now, if you're doing the multi-image document that I posted in there, you would now move to the, you know, second sheet, second diagram there. It'd be the top right. And we're going to do helium. So helium has 2 electrons. Remember that each orbital can hold 2 electrons. So in 1s, there's room for 1 more. So we're going to put the other electron in there. So now helium would have 2 electrons, and the configuration would be 1s2. All right. Okay, now comes the next one. Lithium, 3 electrons. Now we can put 2 in level 1, in sub-level 1s, I'm sorry, but that's it. We don't have any more room. So that means that now we have to do the next available subshell, which is 2s. So we will put the 3rd electron in there. And again, you can put it spin up or spin down. Notice that in the first subshell here, when we added the 2nd electron, it had to have a different spin. So doesn't matter which one we started with, the second one we added had to be of the opposite spin. Okay, so we have now the configuration for lithium, 1s2, 2s1, all right? Okay, next one will be beryllium with 4 electrons. Again, we'll put 2 in 1s, and then we'll have 1 in 2s, and now we have the 4th one. Again, we can still put 1 electron in 2s, but it must have the opposite spin to the first one. And so the configuration for beryllium would be 1s2, 2s2. Right? Okay, you can go to your next diagram. And now we're going to put in boron with 5 electrons. Once more, we put the first 2 in 1s, and that's full. 2 more in 2s, and now that's full. And now we have 1 more electron. We have to go to the next subshell, which is 2p. There are 3 orbitals in there. All of them have the same energy. So technically, it doesn't matter. I can put my 5th electron in any one of those 3, and I can put it in any spin orientation that I want. I'm going to put it on the left one just because my brain reads from left to right. Just keep it simple like that, right? So the configuration here would be 1s2, 2s2, 2p1. So boron has 1 electron in the 2p subshell. All right, Here comes carbon. All right. Carbon has 6 electrons. So once more, we'll put 2 in 1s, 2 in 2s. Number 5 can go in 2p. And now we have a choice to make. We had to put one more electron. Do we put it right next to the first one that we had in there? Or do we put it in a different orbital in the same subshell? Okay, so the first rule was Aufbau. You build from the bottom towards the top, from lower to higher energy. The second rule is called Hunds Rule in honor of Friedrich Hund. And it says that the most stable arrangement of electrons in subshells is one with the greatest number of parallel spins. That means that if I want to put another electron with the same spin as electron number 5, it has to be in a separate orbital. In other words, I'm going to put it there. I could have put it on the right-hand one. That's fine. Another way of saying this is that as long as there are unoccupied orbitals in a subshell, you have to start by distributing electrons into the unoccupied orbitals before you start pairing them up. All right? So carbon would have a configuration 1s2, 2s2, 2p2. However, notice this. The electron configuration only tells me that there are 2 electrons in the 2p subshell. It doesn't specify which orbitals they're in. All right? So that's one of the shortcomings, or let's say the shortcomings of an electron configuration. I mean, it's convenient to write, but it doesn't give you the whole information. Okay, let's do nitrogen now. That'll be the next one. Atomic number 7 has 7 electrons. Again, 2 in 1s, 2 in 2s, and now I have one still unoccupied 2p orbital. So I'm going to put 1 electron in the first one, 1 in the second one, and I'm going to put my 3rd electron in there. Notice that arrangement. There are 3 orbitals. All 3 of them are partially occupied, 1 electron each. So that means that my electron configuration would be 1s2, 2s2, 2p3. And again, notice that the 2p3 tells me there are 3 electrons in there, but I'm going to have to make the deduction that because there's 3 of them and there's 3 orbitals, they must be in separate orbitals. The electron configuration doesn't specify that. All right, next one, oxygen. Now we have 8 electrons, so 2 electrons in 1s, 2 electrons in 2s, and then we're going to put 1 electron in each one of the 2p orbitals. And now there's no more 2p orbitals, so now I have to double up one of them. So my 8th electron is going to have to go into one of those. It can be any one of the 3. I'm going to pick the one on the left, but the thing you have to make sure of is that you put an opposite spin on it, okay? So electrons can be paired, but they had to have opposite spins. Otherwise, they would not have a unique set of the 4 quantum numbers. The configuration then would be 1s2, 2s2, 2p4. Notice the 4 electrons in the 2p subshell. You have to kind of like, infer that you have, one of those orbitals must be occupied completely. Okay, we got fluorine, we're almost there. Fluorine, 9 electrons, again, 2 in 1s, 2 in 2s. And in the 2p subshell, I have 1 occupied orbital. So I'm going to go to the next one. I'm going to put the 9th electron. I'm going to put it paired up with, I'm going to use the middle orbital here. I could have used the one on the right, doesn't matter. And I have an electron configuration of 1s2, 2s2, 2p5. Again, notice the 5 electrons in the 2p subshell. Okay, this is going to be our last one. We're going to do neon, 10 electrons. Again, 2 in 1s, 2 in 2s, 2 in one of the 2p orbitals, 2 in the other 2p orbital, and now I have 1, which would be number 9, and then my 10th electron has to fill up that final 2p orbital. Notice that when we write the electron configuration, we can see that we have 1s2, 2s2, 2p6. There is no more room in any of these subshells. In other words, the 10 electrons of neon essentially are filling up 2 levels here. it makes you wonder, could this be the reason why neon is one of those so-called noble gases that do not react with anything else, don't form compounds? Could it be that a completely full set of shells is what makes these things stable? Okay, well, hold that thought. And it's something we'll tackle probably in the next lecture. Okay, so let's practice here. I'm going to have you guys practice now. What would be the electron configuration for magnesium, right? We only went up to number 10. So magnesium is what? Number 12, right? So 12 electrons. So let's remember the order in which we'd be filling these up. So we go 1s, 2s, 2p, 3s, 3p, and then 4s. Remember, after 3p comes 4s, not 3d. So what I'm going to do is I'm going to put 2 electrons in 1s, 2 electrons in 2s. 2p has room for 6. I'm going to put 6 in there. And I think that completes 10. So the other 2 can fit into the 3s subshell. There we go. Just to be sure, make sure you add up those superscripts. They need to add up to the total number of electrons. 2 plus 2 plus 6 plus 2, that's 12. Okay, so we're good. We didn't make a mistake. Now, when you look at that configuration, you notice that for levels 1 and 2, neon had a configuration that was 1s2, 2s2, 2p6. So you could envision magnesium as being built like this. I have a nucleus with my 12 protons, and then I put in a prefabricated shell or core of 10 electrons, just like neon, to which I then added 2 extra electrons. So I could write this configuration in this form. I put a bracketed neon symbol and then add just the ones that are different, the 3s2. This is called the abbreviated electron configuration. And as you can see, you know, it's a little shorter than this. So when we get to big atoms, you know, this might come in handy. Right now, it's not a big deal, but it's kind of useful because it helps us write things a little easier, right? Okay, so we got that in there. Remember, this doesn't mean that magnesium is a neon atom with 2 extra electrons. It is not, because the nucleus has 12 protons. Neon's nucleus only has 10, right? So that's not what it means. This is only about the electron configuration. Okay, now let's do this. What would be the possible quantum numbers for the last, the outermost electron in chlorine? In other words, if I were building the Anbau diagram of chlorine, when I put that last electron in there, what could be some possible quantum numbers? All right. So let's play with this for a moment here. All right. Let's see. So chlorine has 17 electrons. That's the atomic number, right? And again, remember the order in which we're going to be filling these things. So I can fit 2 electrons into any S subshell and 6 electrons into any P subshell. So I got to start adding them, you know, according to the capabilities, up to 17. So I would get 1s2, 2s2, 2p6, that's 10, 3s2, that's 12. I have 5 more. So I have room in 3p for up to 6 electrons, but I only have 5 left over. So again, make sure you double check your numbers here, right? 2 plus 2 plus 6 plus 2 plus 2 plus 5. That's 17. Okay, so we've got the complete complement of electrons here. Now, if I had done this on a diagram, I see that the last electron I added here was in a 3p orbital, right? Remember that we had an option when we were building those, you know, p orbitals to put the electrons, you know, wherever we wanted. So there is going to be 2 filled orbitals, right? And 1 partially filled orbital. So 1 electron is going to be sitting alone in one of those 3 orbitals in this 3p subshell. We don't have a way of telling where it is because we arbitrarily fill in the diagram from left to right, but we didn't have to do it that way. So that means that the last electron has to be in a 3p orbital. So, okay, so what do we know? We know that according to this, n has to be equal to 3, because that's the level. If it's a p orbital, L has to be equal to 1. That means that you could be in any one of 3 orbitals with the numbers -1, 0, or +1. And don't forget, that electron could be spin up or spin down. So if you're going to come up with what are the possible numbers, you can tell there's more than one possibility. Let me see if I can write here on the screen without messing things up. So for example, you could have a set of numbers 3, 1, -1, and 1/2. So that could be one set of numbers. Now what I'm going to do is I'm going to vary the last one. So another puzzle would be 3, L equals 1, ML equals -1. And now I could say the spin number is spin down. Remember, that electron is sitting alone in that orbital. It's nothing to say it has to be spin up or spin down. It could be either one. So that's 2 possibilities. So now what you can do is you can go on doing this, right? And now you can vary the value of ML. So go 3, 1, 0, +1/2, 3, 1, 0, -1/2, etc., etc. So I think you should be able to find a total of 6 possible sets of quantum numbers for this guy. And it kind of reinforces the whole idea of the uncertainty, right? We don't really know. We don't have a set, precise, exact number for this guy here, okay? All right, the last thing, pretty much the last thing I want to cover here is the following. Remember that we said, just for the sake of illustration, that the spin number represents the kind of like the magnetic field generated by the spinning of the electron. Now remember, this is just an analogy. There is no such thing as the spinning of an electron, but we know that in measurements, it shows that electrons can have either +1/2 or -1/2 quantized values for this property. And this is an intrinsic property of the electron. So we say typically that, the spin points towards the north pole of this magnetic field. So you can see on the left side here, you have 2 electrons, both of which have a, +1/2 or like an up spin. And then the one on the right, one electron is spin up, the other one is spin down. Now, because these are magnetic fields, what we would say is that the one on the right, essentially, the magnetic field generated by one electron spin essentially cancels out the magnetic field generated by the spin of the other one. So we would say that the one on the left, where the 2 spins are in the same direction and therefore the 2 magnetic fields are not canceling each other, we would call that a paramagnetic arrangement. The one on the right, where the magnetic fields cancel each other, we would call it a diamagnetic field. Now, diamagnetic arrangement. So notice that it all has to do with whether electrons are paired or not. So when we built the carbon atom, remember we arrived at where the last 2 electrons were placed in separate orbitals in the 2p subshell. Those 2 electrons are placed in different orbitals to maximize having the same spins. So because these spins don't cancel each other out, we say they're unpaired. And therefore we have a paramagnetic atom. The one on the right is showing us what we found with neon, where the whole 2p subshell was full. Each orbital has 1 electron with a spin up, 1 electron with spin down. In other words, all the electrons are paired, which means each electron's spin is matched by another electron's, opposite spin. And therefore, all the magnetic fields cancel out. This is called diamagnetic. And it's interesting, but you can do an experiment. And I'm going to show you a sketch. This is not what the machine actually looks like. But the point is this. Let's say that I have a substance that is paramagnetic. And I suspend it from a balance, right? And I approach an electromagnet. here's the thing. If the substance is paramagnetic, in other words, if it has unpaired electrons, that means that it's generating a net magnetic field, right? The electrons are not canceling each other out. So that means that this net magnetic field is going to be attracted, is going to be drawn in by the electromagnet. When it does that, it's going to pull on that side of the balance. And what I can do is I can counterbalance it on the right side and figure out what is the weight that is getting generated here. And by using some, standard classical physics calculations, I can figure out how paramagnetic this substance is, and therefore how many unpaired electrons are in it. Isn't that cool? I think that's a cool experiment. So cool, I've never done it myself because I'm not a physical chemist, but it's a cool experiment. And like I said, this is just a sketch, okay? The actual apparatus doesn't look like this. But in the early days, they would have done something like this and done the same classical calculations because there's a lot of math in electromagnetic theory. All right, so that's what we have. And just want to show up here at the end before we leave. This was a meeting that happened, I believe, in 1927. It was called a Solvay Conference. And here are assembled all of the bad boys of quantum physics. All the bad boys are here. Yeah, man. You might be able to recognize a few of them. I don't know. Well, here's Einstein. You can probably recognize his face, right? Some other ones in there. Let's see. This is de Broglie over here, the guy who gave us the equation for the relationship of the wavelength and the mass and speed of the electron. Here is Niels Bohr over here, right? Here is this is Heisenberg. This is Pauli. This is Schrödinger over here. So anyway, it's a cool picture. I love it.
But I think it is important that we make a correction here when we talk about the bad boys of quantum physics. Who was the baddest of them all? Right here, Marie Curie, first woman to win a Nobel Prize, first person to win it twice, only one to win it in 2 different science categories. Madame Curie, you are the baddest of them all.
All right, guys. Well, that's all we have for this particular presentation. We're going to move on to another one. So let me go here. Okay, so this lecture will be available in your Unit 8 module. So as soon as it's available, I'll post it in there and you can watch it. There is going to be another lecture where we're going to go over the periodic properties of the elements and why the periodic table is periodic. All right. Thank you so much, and we'll see you soon.